With that, we've come to the final talk of this oral session, and I'm inviting Mélissa to start sharing her screen if she's around. Hi, Mélissa.
Yep. Hello.
Mélissa Martinot, she will be telling us about investigating pure anorthosite outcrops. There she is. So you can run your slides, right?
Yeah, I can. Can you see my screen now?
Yes,
or?
we see it and we hear you very well.
Okay, perfect. Thank you.
Perfect. The stage is yours. I'll be up in 10 minutes.
Yep. Hi, everyone. It's nice to be back at ELS after some time. Today, I will present to you the results that the team and I produced as part of my postdoc project at the University of Central Florida. And we're interested in investigating the anorthosite outcrops exposed within impact craters in the lunar highlands using a series of remote sensing datasets. Okay, so in this ternary diagram, the Apollo rocks all plot in this ternary diagram. And from this, the study of those samples, the lunar magma ocean concept was sparked. And the lunar magma ocean concept also predicts the formation of lunar primary crust as anorthosite. And it plots here in this part of the diagram. Anorthosites have more than 90% plagioclase. And this is all great, but what the lunar magma ocean concept doesn't really show is what remote sensing, global remote sensing surveys showed, that there are a lot of heterogeneities at the lunar surface that are not actually captured by the lunar magma ocean concept. And so we aim at trying to provide more constraints on the vertical and horizontal composition of the lunar crust, and particularly the anorthosites. So we're gonna use a lot of, well, as many remote sensing datasets as we can. And today I will mostly talk about the M-cubed dataset, the diviner dataset, and some LRO neck single scattering albedo maps. In future, we plan to also incorporate the magnesium number maps and also Grail crystal thickness models. So first of all, what we want to do is actually to define pure anorthositic areas. And to do that, we use the Moon Mineralogy Mapper, or M-cubed datasets. And all of the squares here are crater selection, and so you can see that they are scattered all around, all across the lunar surface. The crater that I will be focusing on today is Proclus crater, which is this cute little 30-kilometer in diameter crater. Some facts about the M-cubed instrument. So it orbited around the moon between 2008 and 2009 and obtained data between 0.4 and 3 microns, spanning 85 spectral channels and with a spatial resolution of 140 to 280 meters per pixel. And so once we do mosaics over the craters, we actually calculate a series of spectral parameters. And this graph here on the right shows you the color composite that we make using those spectral parameters. So in red, we show the area of, oh, I should also say that this is a beautiful pure plagioclase spectrum with one absorption band here centered at 1250 nanometers. And the color composite is made using the area of the absorption band in the red region as red, in green the area of the absorption band in the green region, and in blue the area of the color of the absorption band in the blue region. In this case, it's non-existent. So we end up with a color composite that looks like this for Proclus crater. So the mineralogical diversity is highlighted in different colors, and so this graph here shows a summary of the different mineralogies we can find here. So in blue, we'll see pyroxene, in green, olivine, and red, plagioclase. So this is all good, but we want to make sure that we actually manually then check every pixel that is highlighted here to make sure that it actually displays the plagioclase absorption band in order to be sure we only map plagioclase. And so this is what we do, and we end up with a map like this for plagioclase areas, pure plagioclase areas. So once again, this is a pure plagioclase spectrum. And yeah, in the case of Proclus, those are the areas where we see only pure crystalline plagioclase spectra. After defining our pure anorthositic areas, we then go in and use the diviner data in order to have an idea on the, well, because it can actually distinguish the composition of plagioclase. It can tell us more about the composition of those areas. And so diviner is a radiometer that is still in orbit today. It started orbiting in 2009, and it acquires data between 0.3 and 400 microns and has a resolution, spatial resolution of about 200 meters per pixel. And the region that is interesting for us is the 8 micron region, because in this region there is an emission maximum that is called the Christiansen feature, and this feature is related to the position of this Christiansen feature is related to the mineralogical composition. And I just want to attract your attention to this graph here to show you that the Christiansen feature, or CF for short, so the CF position of albite and anorthite are different, and those are the two plagioclase emitters. It's also different for pyroxene and olivine. Okay, so this is a map that shows all of the hues that go from yellow to green are pixels that are plagioclase compatible. So this is a corrected Christiansen feature position map. And we just masked out all the values that are below 7.35 microns and above 8.06 microns, and we just end up with plagioclase compatible areas. And when we then look at the histogram or the distribution of the CF position, we end up with this. And so we have quite a large range of values that are displayed in Proclus. But the median is at 7.95 microns and the average at 7.92 microns. And this is consistent with immature calcium-rich plagioclase to mature plagioclase compositions. So after looking at the diviner perspective, we move on and actually want to know about the single scattering albedo of pure anorthositic sites, because they can just tell us more about those interesting areas. And to do this, or actually someone from my team made the photometric processing using LVROC NAC data. So LVROC NAC data are also orbiting on lunar reconnaissance orbiter, and it's still in orbit today. It has a resolution of 100. What? No, it's not 100 meters per pixel. Sorry about that. Okay, I don't know why I wrote this. But the photometric processing actually consists of 3 main steps. So first, stereo pairs of NAC images are selected and map projected using ISIS. Then DTM, or digital terrain model, is calculated using the NASA Ames stereo pipeline. And finally, the MATLAB optimization tool is used in order to solve simplified Hapke equation that derives the albedo and reflects it over MAC images. And so here, this is a single scattering albedo map for South Ray crater. This is just to show you that we benchmarked the study using other studies. So we obtained, again, I should say that the blue region here is the region where we observe pure plagioclase spectra, pure crystalline plagioclase spectra. And we obtain median values between 0.69 and 0.73, and average values between 0.67 and 0.07. And previously, Ryan-Fleck, Watkins, and collaborator obtained similar values, although they are a bit lower. But this could be due to variations in boulder count and maturity. Okay, so this is the single scattering albedo map for Proclus. So again, this is the area where we see pure crystalline plagioclase spectra using M-cubes, and the single scattering albedo value that we obtained. So the median values are between 0.74 and 0.81, and the average between 0.75 and 0.79, which is higher than, previously thought for pure anorthositic areas, but this is a very immature site. So just as a summing up of everything, the initial results of our study show that there is a good general agreement between M-cubed pure anorthositic areas and diviner plagioclase compatible extents, although the diviner plagioclase compatible extents are often wider than the M-cubed areas. And preliminary photometric processing is consistent with previous analysis of pure anorthositic areas, although we are working with more immature terrains than previously analyzed, so we have higher values. And yeah, so for now we studied craters that are, sampling depth between 4 and 27 kilometers into the crust, but we're just going to extend this once we study more craters. So stay tuned for more results, hopefully soon. Thank you for your attention.
Perfect. Thank you very much, Mélissa. Are there any questions for Mélissa from the audience? If I'm not wrong, Mélissa, I think I remember that Proclus crater was interpreted to have brought deeper seated crustal material to the surface. Is that consistent with what you're seeing in the spectra?
So we see very wide areas of beautiful pure crystalline plagioclase spectra, which actually the crater isn't super large, so it should be crustal material. Yes. And it's, so the spectra are beautiful. It's one of the most pristine plagioclase spectra that you will find on the lunar surface.
Does it also have to do with the fact that the crater is expected to be fairly young?
Yeah. It must have so because it's pretty immature, then space weathering didn't have time to, kind of erase everything. So we still have a view of pristine plagioclase spectra.
Great, thanks.
Stop sharing. Yes. And yes, thank you, Harry. I know 100 meters is the WAC camera resolution. I don't know why I wrote this on the on the slide.
I know that you know.
I was like, what?
It was probably a typo, no problem.
Yeah.
So. Of course you know. Thank you for the really interesting talk.
Oh,
So
thank you.
appreciate it.